Welcome to S2C video series. I am Ashok Kulkarni and I will be your presenter today.
This video begins with a short introduction to S2C, the product offerings, followed by demonstration of multi-FPGA debug capability and high-speed data transfer between design and verification environment. S2C was founded in 2003 with headquarters in San Jose, USA. Currently, S2C offers fourth generation prototyping solutions. We have sold about 400 prototyping systems with over 80 customers worldwide. S2C offers a complete suite of FPGA-based prototyping solution that consists of hardware platform, software tools, and accessories and prototype-ready reference designs to quickly begin exploring the tool flow and its capabilities. The prototyping systems are available in different configurations such as single, dual, and quad FPGAs to meet different design needs and support both Altera and Xilinx FPGAs. Now, before we discuss the demo, let's take a quick look at the verification module. The verification module consists of a single Statix 4 GTX 180 or GTX 360 FPGA and can be used in one or more of the following three modes: logic mode, verification mode, and debug mode. In the logic mode, the verification module can be used as a standalone logic module for prototyping designs up to 3.2 million AC gates. Today, our focus is on verification and debug mode. The demo shows two key capabilities of the verification module. One, high-speed data transfer between design memory and verification environment. Two, multi-FPGA debug capability. The demo hardware consists of a quad Statix 4 prototyping board, verification modules VM1 and VM2, Altera USB blaster cable, by4 PCI Express Gen 2 host adapter and PCI Express cable. The software includes Altera Signal Tap for debug and S2C type player for creating the FPGA bitstream all the way from RTL to FPGA configuration files. VM1 and VM2 are identical. The reason for using two VMs is to show multiple demos without switching the VM modules between the demos. The demo hardware setup shown here is identical to the actual setup. So let's go and take a look at the actual setup. This is the entire demo hardware setup. As you can see, it consists of a quad Statix 4, VM1, the verification module, VM2, the second verification module. You will notice that they're all connected to a standard PC power supply. Let's get closer to VM2. VM2, as you can see, is connected to the PCI Express interface through this cable, which is connected into the PCI Express host adapter that is located in the PC. Both VM2 and also the VM1 are identical, and VM1 is connected to a Altera blaster cable, Altera USB blaster cable, and the other end is connected to the JTAG. That's how the programming is done. So let's also take a quick look at the switch 5, which will be used in the that is the switch 5 there. Demo 1 is part of high-performance data transfer between design and verification environment using the PCI Express lane. This demo uses verification module VM2 and Quad Statix 4 prototyping system. Quad S4 consists of FPGA 1 through FPGA 4, also referred to as U1, U2, U3 and U4. PCI Express core and DMA controller logic are implemented in VM2 FPGA. The demo design consists of color bar generator logic implemented in each FPGA U1 through U4. However, the logic is different in one aspect: clock speed. Each FPGA generates color bar data at different speeds. U1 generates data at the lowest speed, U2 is faster than U1, U3 is faster than U2, U4 is faster than U3. At any given time, one of the 4 FPGAs writes data into the dual-port RAM memory of VM2. The choice as to which FPGA is allowed to write data into dual-port RAM is determined by a 4:1 mux implemented in U1 FPGA. The select control signal on the mux is generated by the push button SW5 on Quad S4 and is controlled by the user. The color bar data is read by a C API program in PC, which also acts as the PCI Express root complex and displayed using DirectX render technology. The SD card automatically downloads the color bar generator design into each of the 4 FPGAs on power on. Likewise, the PCI Express core and DMA controller logic is automatically downloaded into the VM2 FPGA through the onboard flash memory. Now let's launch the color bar generator program. This program running on the PC acts as a root complex and starts communicating the endpoint device, which is VM2, via by4 PCI Express Gen 2 lane. As mentioned earlier, the program reads data from the dual port RAM and starts displaying using the DirectX render technology. Let me push the SW5 push button, which is the select control for the mux. You will notice that the speed of rolling display changes as I keep pushing the push button SW5. We also have a freeze state to indicate that no FPGA is selected. This shows that every time the SW5 is pushed, the data from different FPGA running at different clock speed is written into the dual port RAM. Now, in the next demo, we'll look at how we can measure the performance of the data transfer. The goal of this demo is to measure the PCI Express channel bandwidth. This is an Altera reference design modified to run on Statix 4, GXT 180, 230 or 360 FPGA. This demo uses verification module VM2 only. VM2 acts as a PCI Express endpoint device. The PCI Express and DMA core logic are mapped to the FPGA on the VM2. PC acts as the root complex that generates, read, write, and performs DMA operations. The root complex sends random data to VM2, which is written into and read from the FPGA block RAM through the DMA controller. The performance is measured by performance test measurement tool from Altera. Now let me launch the performance test program provided by Altera. The performance test program tool allows users to do multiple things: scan for both settings of the PCI Express motherboard, scan and display endpoint device properties, in our case the PCI Express core in VM2 board, allow data transfer from root complex to endpoint devices and vice versa, measure and display data bandwidth. To measure the PCI Express channel bandwidth, first move the slider all the way to the select Run on chip memory DMA test. You will notice you have different menu options as I move the slide bar. Here you can select the DMA test sequence, which can be read only, write only, or write and read operation. Let's choose write and read, that is FPGA to PC to FPGA, which means FPGA writes into PC, FPGA reads the data from PC and compares the write and read data. In the Run on-chip memory DMA test window, click on the continuous loop box so that the operation of read and write keeps repeating. Click on the chip memory test. Now you will notice the channel bandwidth displayed in megabytes per second. You'll also observe a rolling display showing the performance of the DMA read and DMA write operations, which is over 1400 megabytes per second. This is equivalent to 11.2 gigabit per second. This rate compares to the Gen 2 by 4 PCI Express bandwidth. The performance degradation is due to efficiency of DMA controller, PCI Express core, and the PCI Express data packet size. It may be noted that there is no hardware limitation for slower performance. Again, you can select a different sequence from the sequence menu and continue to run on-chip memory DMA test. This demo starts with a quick overview of TypeLayer Pro software and shows two key capabilities of verification module. 1. RTL debug. 2. Debugging multiple FPGAs simultaneously. The demo uses verification module VM1 and Quad Statix 4 prototyping system. The same color bar generator design used in the demo 1 is used in this demo as well. The color bar generator is mapped to each of the 4 FPGAs. The probes are set at the RTL level and the design is debugged in Altera Signal Tap. Let us take a look at the TypeLayer Pro software. TypeLayer Pro is a fully integrated tool that takes an RTL as input and generates a bit stream that can be downloaded into the FPGAs. RTL design can be in VHDL, Verilog, mixed or EDIF formats. The tool works transparently with vendor tools such as ISC, Cortex and third-party tools for synthesis and place and route. With TypeLayer Pro, you can partition a design into multiple FPGAs by simply selecting the logic, dragging and dropping into the desired FPGAs. The partitioning can be done completely automatic, semi-automatic, that is partially guided by user, or manual, that is fully guided by user. The software makes debugging an easier task. This is because it allows you to set debug probes at RT level. These debug probes can then be brought out at the I/O level or into verification module for further debug and analysis. It's very important to note the original RTL names are maintained at the gate level. The tool also allows users to generate programmable clocks. These clocks, as you can see, are generated into a user GUI by simply selecting the base clock and entering the desired frequency. The tool then automatically generates and routes the synchronized clocks to all FPGAs simultaneously. TypeLayer Pro also provides comprehensive board diagnostic tests to quickly isolate board issues, if any. Under the Tools menu, launch the test zone. Select the desired LM board and run various tests. It provides a complete log of the tests and specifically points to the pin pair if there is an error. Once the probes have been selected, you can launch the VM debugger from the Tools menu. Now, when I click OK, the VM debugger automatically launches the Altera Signal Tap. Now, before we run trigger analysis, we need to first download the debug part of the logic into the VM1 by using Altera USB blaster cable and selecting the device and running the download option. While the download is in progress, let's take a look at the probe signals and where you can set the trigger conditions. On the left, as you can see, these are your trigger debug probes at the gate level, and on the right in the red are the trigger conditions where you can change the values depending on the trigger condition you would like to set. Let's go and take a look at the data where we actually trigger and capture. Here, as you can see, we're going to apply a trigger. Once I apply the trigger now by clicking on this icon, yeah, it triggered and captured the signals. Let's see where exactly the trigger took place. Right here. So you can notice that these are the various trigger conditions corresponding to the RTL probes. If you look here, these are exactly the trigger conditions corresponding to the RTL names. Now, one important thing to remember, these debug probe names are exactly the same as the one you saw in RTL. So let's go to the Type Layer Pro and look at that. Let's close this. If you remember, this is where we set the probes at RTL level. These names, as you can see, are exactly the same as what you would see at the debug level, that is at the gate level. So there are two key points to remember in this demo. Number one, we have RTL debug capability. Number two, we have the multi-FPGA debug capability. It may be noted that SignalTap allows you to debug one FPGA at a time. Verification module eliminates that limitation and allows you to debug multiple FPGAs, 4 in the current demo, simultaneously.
In this video, we showed you that S2C offers a complete solution for rapid prototyping ASIC and SoC with hardware, software, debug and verification. The verification module allows debugging multiple FPGAs at RT level and enables large data transfer between design and verification environments. To learn more, go to www.s2cinc.com.